Great. Well, welcome everybody today. We are very excited to have Christian Hemming from ETH Zurich presenting today. Christian will be presenting Posterior Meta Replay for Continual Learning, a paper that was co-authored with Maria Severa and others. Christian is a PhD graduate now from ETH Zurich. He will be there for 3 more days. He is an author on many works on uncertainty, OOD, and continual learning. The work he's presenting today was from NeurIPS 2021, and I guess we're very excited to hear from you, so please take it away, Christian.
Thank you so much. Thank you so much for organizing and for inviting me and for giving us a chance to present our recent work. So I guess most of you know why we're here and what's the topic. So when we learn in connectionist networks, and for some reason we only have some of the data available, and at some later point more data becomes available, and we want to update the model for efficiency reason only on this data, there's this problem of catastrophic forgetting. And for that reason, we develop continual learning algorithms that should cope with this problem along with a lot of other useful desiderata. And what we study in this paper is this way of continual learning that's commonly studied in literature, where we consider a discrete set of tasks. And I will now, in the next 2 slides, try to formally introduce this setting, just to be very clear about what we are considering as continual learning, but don't be scared. Later, I will try to present everything with concepts and illustrations. Okay, so for each task, we consider, or we assume that we have access to an i.i.d. dataset, and each task has some unknown underlying joint distribution. And then when we do discriminative modeling that we consider here, for instance, classification or regression, what we're interested in is learning this conditional. And we can easily do this with having this dataset. Now, we're not interested in these task-specific conditional models. What we're interested in is to build a discriminative model from the unknown joint that is composed out of all these task-specific joints. So we're interested in this guy. So maybe to make it a bit more clear, let's consider the problem of split MNIST. What we can easily do is learn a task-specific discriminative model. For instance, a binary classifier for each task in the continual learning setting we're considering. But at the end, what we're interested in is to have a discriminative model that can distinguish all 10 classes. And so while we can easily obtain these guys, this term is pretty difficult to obtain. And for instance, recently last year, there was a paper by Guido van der Ven where he proposed to learn generative models that allow you to estimate these densities. He proposed it for individual classes, but it's the same if you do it for individual tasks. And then you can just evaluate this formula in closed form. What we do instead here is we make an additional assumption. We assume that the support for the input distributions of different tasks are disjoint. And when we make this assumption, then this term is either 0 or 1, and it's only 1 for one task. And then we have this problem of task-inference. And so when we are getting an input, we need to decide to which task this input belongs. And then we can use the task-specific conditional in order to make a prediction. So I hope this will become clear throughout the presentation. And the presentation will be structured in the following way. What I do first is I talk about an older work of ours where we propose to use hypernetworks for continual learning. And the reason why I do this is because our new paper can be essentially seen as a probabilistic extension of this older framework. And then I talk about Bayesian continual learning, about the challenges and promises that come along with this framework. In order to set the stage then to talk about our work, which I will first explain to you, and then I show you also some results. Okay, so let's start with the first part. And therefore I need to introduce to you the concept of hypernetworks. So assume here we have some kind of main network as we are used to in machine learning. So we have some neural network that processes inputs X to give us predictions Y. And now commonly this network has parameters W that we are trying to learn. Now a hypernetwork is an additional neural network with parameters psi And now the goal of the hypernetwork is to output the parameters of the main network. So we're not learning the parameters W of the main network. Instead, we're learning the parameters psi of the hypernetwork. And hypernetworks have been used in a lot of applications in between. In the meantime, we are obviously now interested in continual learning. But what's important to note is when David Ha introduced it in 2017, he was interested in weight compression. And intuitively, you might think, okay, because I have to produce such a high-dimensional output vector, this network is going to be massive. But you can actually design these network architectures such that the number of weights that you need to learn, i.e. psi, is lower than the number of weights that you produce. And we are always considering this compressive regime here for fairness when we compare to other models, other methods. And the purpose of these input embeddings will become clear in the next slide. They will index tasks in our case. And if you allow me to do some advertisement, we recently published a package called hypernetworks, where you can easily explore, if you have any ideas regarding hypernetworks, you can easily explore them in PyTorch using this package. Okay, so let's go back to split MList. One way to learn each of these tasks is, of course, you could learn a separate model for each of them. But then you need a new neural network every time you learn a new task. What we propose in this paper is to instead use a single shared meta model, the hypernetwork, in which you entangle all of these task-specific models. And then by inputting the right task embedding, you get the right model for doing predictions. Now, there are two problems with this framework. Now there's again a single model that you need to learn continually. So you still need to address this problem of forgetting. And I will show you on the next slide how you can easily do this at the meta level. And then I need to know when, for instance, you get a 4 as input, you need to know that you need now to choose the green task embedding in order to make prediction. And we call this problem task-inference, and we will talk a lot about this problem today. Okay, so here's again a sketch of our hypernetwork that produces the weights of the main network. And now let's assume we want to continue to learn these three polynomials. And we start with a random hypernetwork, here illustrated by a one-dimensional embedding space and a one-dimensional weight space. In practice, this will be low-dimensional, like 8 dimensions or so, whereas the weight space can easily be millions of dimensions. Okay, now when we want to learn the first task, we need to find a weight configuration for the first input embedding that solves this task. Now, when we continually learn and want to learn the next task, we can freely change the hypernetwork function. The only thing we need to make sure is that the single input-output embedding, the single input-output mapping stays fixed. And this already shows why continual learning at the meta level is simpler, because now we just need to ensure one input-output mapping stays fixed, whereas at the main network level, we would have needed to ensure that this infinite amount of input-output mapping stays fixed. Again, now when we continue learning the next task, we can freely change the hypernetwork function. We just need to make sure that these two input-output mappings stay fixed. And this already motivates a simple regularization that we proposed. You can either sum over all previous tasks, or you can also, because you want to avoid this linear sum, you can also just stochastically choose a previous task that works equally well. And then you want to make sure that the output of the hypernetwork for this previous task doesn't change compared to the output of a hypernetwork that you have checkpointed before learning the current task. So you need to checkpoint every time before you start learning a new task, you need to checkpoint once the hypernetwork. So you have one checkpoint always in memory. That's very similar to other regularization approaches like synaptic intelligence, online EWC, and so on, where you also need to store one previous model for regularization. Okay, so now we know how to entangle all the different task-specific models into a single hypernetwork without suffering from forgetting. The interesting question is now, how do we choose the right task embedding when we want to make predictions? So when I see a 2 or a 3, how do I know that I need to choose the second task embedding? And in this original work, we consider multiple ways of how you can do continual learning with hypernetworks, some of which don't require explicit task inference, but we also propose 2 ways of how you can do explicit task inference. And one of these approaches is based on replay-based task inference. In this case, a series of generative models is entangled into a single hypernetwork. But I'm not interested so much in that today. So if you're interested in that, please check out the old paper. The interesting part for today is the second thing we proposed back then, is if you do uncertainty-based task inference. And I think back then we were the first ones who proposed this approach. You would just choose the task embedding that leads to lowest predictive uncertainty. And if that's not clear to you yet, don't worry, because we discussed this approach later in detail. Okay, so now that we have an idea of how you can do continual learning with hypernetworks, let me quickly introduce to you some concepts from Bayesian continual learning. When we apply Bayesian statistics to deep learning, what we're interested in is this application of Bayes rules, usually. So there's this prior distribution. So you define a prior distribution over the parameters of the network, which then induces via the architecture a distribution over functions. And ideally, you encode useful prior knowledge into this distribution. For instance, you want to encode inductive biases that lead to good generalization and so on. And then from this distribution of functions, via the likelihood, you can choose those that model the data that you're observing well in order to form the posterior. And this likelihood, this is just a shorthand for this notation. You just all the data that you have seen, you assume is conditionally independent from given the parameters that you're seeing. And this is just defined via your neural network. So you have a neural network with parameters W, input X, and it gives you some distribution over the outputs. Okay, so maybe to give an illustration, assume you define a prior that induces functions like this. So you have a very rich set of functions. And then the moment you're seeing data, you select via the likelihood those functions from the prior that fit the data well. So here you can see that by squeezing the uncertainty where you have seen the data. Now, interestingly, you can use this formula recursively. That's why it's very interesting for continual learning, because now what you can do is you can use the posterior of the previous task as a prior for the new upcoming task to form the posterior over all tasks that you've seen so far. And because now all the prevention of forgetting is concentrated in the prior, these kind of methods based on this idea have been called prior focused continual learning methods. That's the terminology I also use today. And what's interesting about them is now, no matter in which order you see the data, you don't need to have the data all available at once. You always end up with the same posterior. And that's what makes it so powerful. Maybe to give you an idea of how you can use all of this in deep learning, here's a standard neural network. And what we usually do is for each connection in a neural network, we try to set a single numerical value. And that's what we're learning, to set a single weight to each connection. In Bayesian deep learning, we're trying to find a joint distribution over the weights, here illustrated by showing the individual marginals. And then when you do prediction, what you can do is you can average over all these models that you can get from the joint. And what's apart from many other interesting advantages, what's interesting is that this approach allows you to exhibit knowledge uncertainty. So usually we see a finite amount of data, and we shouldn't commit to a single function from only seeing this finite amount of data. And the Bayesian approach allows you to reflect the uncertainty about which hypothesis you should pick in your hypothesis space based on the data that you have seen. And the other cool thing that I've shown you in the previous slide is that there's now a theoretically sound way of incorporating new evidence. And so you don't need to have a big i.i.d. data set available all at once. You can literally see chunks of it continually and then still form the same posterior, at least in theory. And now comes the big problem. Bayesian inference in neural networks is intractable. And so you have to replace these posteriors with approximate posteriors. And there's a lot of problems associated with it, as I will try to illustrate next. So how can you do approximate inference? Here's a simple example. One way of doing it that's commonly done is to use variational inference, where you try to find a distribution, a parametric distribution closest to the unknown posterior. And you can actually find a tractable optimization criterion that doesn't require you to know this unknown posterior. And one way to choose this Q theta is, for instance, to do such a mean field approximation, where you assume all the weights are independent, and for each connection, instead of learning a single weight value, you learn the mean and variance of this connection. And then by using the reparameterization trick, you can just use the mean and variance and some noise to sample weights from this distribution. And here's, for instance, the kind of approximations you can obtain. You can get something like an axis-aligned ellipse in one of the modes of the quant truth posterior. And an algorithm that allows you to find an approximation like this is called Bayes-by-Backprop. And it has also been applied to continual learning, for instance, as part of the variational continual learning method. So, okay, again, the big problem that we now have in Bayesian continual learning is that we need to do approximate inference. And what I now want to illustrate to you is why this is so harmful to the idea when applying this framework to continual learning. What we illustrate here is a two-dimensional weight space, and in this light green, you see all the parameter configurations of the neural network that perform well on the dataset of task 1, and in orange, you see all the weight configurations that perform well on the dataset of task 2. Now, while learning task 1 or wasting the data of task 1, we don't know about the orange area. And now we need to form an approximation, for instance, putting this ellipse into one of the modes of the posterior. And now, again, we can apply the Bayesian recursive update, but now with these approximate posteriors, when seeing then task 2, we need to shrink the prior of the previous task to be to also fit the data of task 2. And for instance, we could obtain this brown area here. Now, don't forget, all these overlap regions you see between the light green and the orange area are weight configurations that perform well on both tasks that you have seen so far. And our approximation is just this brown ellipse here. And now you can already see the problem. If there's, for instance, as a third task, this area would come up. If you have all data available at once, it would be very easy to figure out, okay, I should pick one of these weight configurations which lies in the overlap of all 3 tasks. But now, since we apply this continual learning approach, our approximate posterior is this brown area, and there's no way, because it's not part of the prior, I can pick this hypothesis. So this shows why it is so difficult, or should kind of illustrate why it is so difficult to use this recursive shrinking of the prior for continual learning. And here, for instance, even for toy examples like this, where we try to learn a sequence of polynomials using a single shared posterior, when learning, either you are still able to learn a new task but have a lot of forgetting on the previous tasks, or if you want to keep the previous tasks, you're not really able to learn a new task. So it's very difficult to actually use this idea in practice. And this is just because of this recursive amplification of approximation errors, because you use approximate inference over and over again. Okay, so with that, what I've shown you now is how you can use hypernetworks for continual learning. So I've shown you how you can easily prevent forgetting, but you have this problem of task inference that we need to tackle. And as an alternative, I also showed you Bayesian continual learning, where the predominant way of doing Bayesian continual learning is this prior focused kind of learning, which suffers a lot from the use of approximate inference that is unfortunately necessary. And now we want to combine ideas from both of these to look into our new paper, which we call Posterior, or the framework, which we call Posterior Meta Replay. So let's look at this illustration again. And again, when we're trying to find a shared posterior, we're interested in these overlap regions of tasks. But due to the use of approximate inference, as I tried to illustrate to you before, it's very difficult to find these overlap regions recursively, because if, for instance, the situation is like this, then you're stuck in one mode and you can't, when the data of task 2 becomes available, you can't find overlap regions with your approximation anymore. Instead, what we propose is to use a separate posterior per task-specific posterior. So you first learn an approximation to the posterior of task 1, and then independent of that, you learn an approximation of the posterior of task 2. And there are now two challenges arising. The first is, again, how can you continue to learn these task-specific posteriors in a non-trivial way? And then, how do you know which posterior to use for making inference? So let's at first tackle the first problem. Again, we use the hypernetwork. But now, instead of outputting the parameters of the main network, we output the parameters of an approximate posterior, as shown here. And then we can sample weights from the approximate posterior to do inference in the main network. And partly for fairness, again, we always make sure that the number of learned parameters in our framework is always smaller than the number of parameters that is available in the main network. So what is this weight generator? Actually, you can choose it very flexibly, and we also look at a variety of options in the paper. For instance, you could say, okay, theta are again the parameters of a mean field Gaussian approximation. And then you can use the reparameterization trick, as I've shown you before, by just sampling some white noise and use the output of the hypernetwork to sample weights of the main network. And in this case, again, the kind of approximations you can obtain are axis-aligned ellipses that live in one of the modes of the posterior. But you can also freely choose something much more complicated. For instance, you could say, okay, the approximate posterior is represented by an additional neural network. So now this neural network here, the weight generator, describes an implicit distribution where some noise random variable is transformed by this deterministic function into a distribution over the weights of the main network. And now the output of our original hypernetwork is just the parameters of this additional neural network. So now in this case, we have a three-stage hierarchy where actually the original hypernetwork now takes the role of a hypernetwork. And now you have much more flexibility, but it comes obviously at a cost. So for toy examples, this kind of approach works extremely well. But then because now for finding this approximate posteriors, you need to do a lot of estimations in order to get optimization objectives. It is much less scalable and becomes much trickier to train the moment you go to more challenging benchmarks. Again, how do we prevent forgetting? It's very similar to what I showed to you before. So we have a task-specific loss in which the data of the current task enters. And this is just to learn the approximate posterior of the current task that we are seeing. And then there's this regularization over here. And again, you can either go over all previous tasks, or equally well, you can just stochastically choose one of the previous tasks. And then you make sure that you minimize some kind of distance or divergence from the current output of the hypernetwork, so from the current approximate posterior outputted by the hypernetwork, compared to the approximate posterior outputted by a checkpointed hypernet. For some, it really now depends on the type of distributions that you choose here. For some of them, you can analytically compute some kind of distance or divergence. If that's not possible, we go from the distribution space into the parameter space and regularize these parameters theta. And here it also becomes now clear why we chose the name posterior meta replay, because what happens here is that we use this checkpointed hypernetwork to replay the parameters of the approximate posteriors at the meta level. But we're not replaying data or anything. So don't forget, we only need the data of the current task. The data of previous tasks never enters our forgetting regularizer. Okay, so now we know how to prevent forgetting, but how do we know which embedding to choose when doing inference? In order to explain that, let me first explain to you what is uncertainty-based out-of-distribution detection. So now when we have the posterior available, we have access to uncertainties. For instance, if we go at an in-distribution location like here, we should have low uncertainty because we have explicitly seen data that tells us how to do predictions here. But then ideally for the problem of OD detection, when we go to an out-of-distribution location, we have high uncertainty. And then by comparing these uncertainties, we can decide that in-distribution points are those that have low uncertainty. There's a lot of problems with this simple assumption that is often made in the literature that we discussed in this paper down here. But now for the sake of this illustration, let's just keep with this simple intuition of using uncertainties for out-of-distribution detection. So how can we do that now for continual learning? Continual learning now in our framework, we have one posterior per task available. And now if we are asking, for instance, how to do inference at this location, we can just check, okay, for the posterior of the first task, for which this input is an in-distribution location, we have relatively low uncertainty, but for a posterior of another task, we have high uncertainty. So in order to make predictions, we choose the posterior that has lowest uncertainty. So at this location, we would choose the blue posterior for making a prediction. So that's the idea how we choose input embeddings when making predictions. Let's look at some results at first, and some low-dimensional problems to get an intuition, so some toy problems. I've shown you before, learning a sequence of polynomials with the predominant way of doing Bayesian continual learning, so this prior-focused way, like EWC, variation, continual learning, and so on, is very challenging. But in our framework, it becomes very easy because you can easily learn the polynomial of each task. You store them into the hypernetwork, and then you can use the uncertainty to figure out which posterior to use in order to make predictions. And also, maybe more interesting, to get an intuition for why we have to maintain parameter uncertainty. Let's look at this toy example where we do classification. Each task is now a binary classification. We had first to distinguish these two modes, then these two, and then lastly these two modes. And again, in our model, we always have one task-specific solution. So what you see down here is the uncertainty over this input space. When we use the deterministic approach I've shown you at the beginning, where the hypernetwork directly outputs the weights of the main network. In this case, uncertainties are only calibrated where we have seen data, and everywhere else they're kind of arbitrary and highly dependent on the architecture. If we use the new approach where we output the parameters of an approximate posterior, we kind of model a distribution over possible decision boundaries, and therefore we get much more robust task inference because, as you see here, now we have high uncertainty on the inputs of all other tasks. So we would know that we should, for input, look, if we get inputs from another task, we shouldn't use this posterior for making predictions. Maybe more interesting, let's look at some results for split cipher. So here we're looking at the cipher 10 dataset, but again, we're learning it continually. At first, we discriminate airplanes from cars, then birds from cats, and so on. What you see here in the rows, the first row is our original approach, where the hypernetwork directly outputs the parameters of the main network. And the second row is our new approach, where in this case now we output an approximate posterior with a mean field Gaussian approximation. What you see here in the columns is when the task identity is given to the system, so we tell the system which is the correct input embedding. During measures plasticity, so how well can we learn new tasks? And final is after we have seen all tasks, how good is our performance still? So the difference between these two is forgetting. And as you can see, both numbers are pretty high, so we have good plasticity, but we also have virtually no forgetting because these numbers are pretty close to one another. Now, more interesting is the case when we have to automatically infer the task identity. And for those of you who are familiar with the continual learning literature, this accuracy would correspond to task incremental learning. and this accuracy would correspond to class incremental learning. So here, this is the full cipher 10 accuracy now, so the 10-way classification. Yeah, and as you can see, we have a lot of benefit from explicitly maintaining epistemic uncertainty, so there's a big jump in accuracy here. And these numbers are quite respectable on this benchmark for continual learning, but they're still quite a drop here. And as you can see, forgetting is not a problem, task inference is the problem that causes this drop in performance. And so you might ask, okay, is this drop in performance because the priors we have chosen lead to uncertainties that are not useful for o.i.d. detection, so for task inference, or is it because we continuously learn these approximate posteriors in a single shared hypernetwork? Does this kind of mess up the posteriors that we're learning? And to control for that, we can just learn posteriors separately. So here in this baseline, just learn a separate posterior for each task. And as you can see, numbers are pretty similar. So it's not the case that uncertainties get screwed up because we have learned them all together in a single hypernetwork. Maybe what's interesting to note is if for some reason it is possible for you to do batch-wise inference so that you know multiple inputs belong to the same task, due to simple statistical effects, you can easily boost task inference accuracy and get much better accuracy. And as a perspective, here are some baselines. For instance, EWC or VCL. Also, these are common prior-focused continual learning methods that are known to work quite bad in this class incremental learning setting. And one reason for that in classification is, of course, also the use of a softmax, but it's predominantly used in most of the continual learning literature, and anyway, all the other literature as well. But also other approaches, for instance, like experience replay, which is it's already a very old, but it is still a very important baseline where you store course sets at each task. So you store data for each task and you replay it when learning new tasks. Also, these kind of baselines don't obtain good performances on a benchmark like this. Okay, so what we see here, again, forgetting is not a big problem. Our problem is task inference. And now what I tried to make clear before, and what you can also read up in this paper from us here in reference 1, is that it's very difficult to set prior knowledge for neural networks such that you have uncertainties that are meaningful for out-of-distribution detection. Now the thing is, the only thing we need is to have high uncertainty on inputs of other tasks. So we don't need to have high uncertainty on everything else, like o.i.d. detection requires, just on inputs from other tasks. And actually, while we're doing continual learning, we're seeing all these different tasks. And so therefore, we also propose a different way, so that we propose a way that allows you to explicitly calibrate the uncertainties of inputs from other tasks. So what we're doing is now similar to experience replay. We store a core set for each task, but we use these core sets for a very different purpose. So now that our hypernetwork is not anymore storing these full posteriors, instead our hypernetwork is continually learning these data reduced posteriors. And after I've seen all tasks, I have these core sets available at the end, and I can construct with them these core sets C-tiled for each task, which always consists of the core set of the corresponding tasks. And I use inputs from all other tasks associated with random labels, such that I can calibrate them to have uniform predictive distribution. And now there's another benefit that directly arises from the Bayesian approach, as I've shown you before. I can always use this new data to update the posteriors in a theoretically sound way. And here, for instance, are some results on a benchmark like split MNIST. This gives a huge boost in performance. So here, again, we are essentially relying on out-of-distribution detection. This is, again, our class incremental learning performance. And then if I do this approach, I get much better accuracies. Okay, but you might say, split MNIST is a very simple benchmark. Also approaches such as experience replay that also use core sets, but in a very different way, perform quite well. But the moment you go to something more challenging, these kind of methods break down, and we are still getting a performance boost. That is impressive, but we're still getting a performance boost compared to what I've shown you before. And again, a lot of why this doesn't work perfectly can be explained because we now have to update our approximate posterior. So we have to once use this recursive update, which suffers from the same problems that I've shown you before, because we're making use of approximate inference. Maybe for the experts, a little note. So that we switch from out of distribution detection to this explicit calibration of uncertainties means that we switch from using epistemic uncertainties to aleatory uncertainties. Okay, with that, I would like to come to the conclusions. So what I've shown you today is that we introduced hypernetworks for the field of continual learning, and I hopefully convince you that for the standard continual learning benchmarks that you encounter, we virtually see no forgetting, but we have limited task inference accuracy. And we propose multiple ways to attack task inference. This replay-based approach I haven't talked about today, but the uncertainty-based approach I think I talked about a lot. And I showed you that if you use the uncertainties that are induced by the parameter uncertainty you get from the Bayesian treatment, then you essentially resort to out-of-distribution detection. And unfortunately, as we discussed in this paper, Bayesian neural networks are not intrinsically good at that. And even in some cases, you can choose priors that are suitable for OD detection. For most real-world problems, it's still unknown on how to choose them. But luckily, in continual learning, the problem we're dealing with is a bit easier. And therefore, on the last slide, I explained to you, you can also use this approach of core set fine-tuning, where you store these core sets. So before, we never had to store explicitly data, but now for this approach, you have to store core sets to then calibrate the uncertainties that you have high uncertainty on inputs from different tasks. But as I've shown you, this approach relies that you use the Bayesian recursive update, which heavily relies on the quality of the approximate inference method you're using. And lastly, I just want to mention that I hope that our work improves or revives the interest or motivates people to look into Bayesian continual learning methods, because as I think, as you've seen throughout the presentation, the Bayesian treatment gives you a lot of benefits along the way. And previously, performance kind of wasn't looking so nice, but we achieved quite good performances with our approach. With that, I would like to thank all my collaborators, again, especially thanks to Maria, with whom I've worked full-time together on this project for a long time. And I thank all of you for your attention, and I'm very happy to take your questions. Thank you.
Thank you so much. That was outstanding.
Thank you.
So yeah, as Christian just said, if you had questions, either ask them on Microsoft Teams, or if you're on YouTube watching right now, please just put it into the chat and I will repeat it here. I have several questions, but I want to see if anyone else has something they want to ask first. I'll go ahead and get started. First, I just wanted to note that the performance you got on CFAR 10 for example with no core set on incremental learning was very, very impressive. That's something I've looked at a lot, is like core set free, rehearsal free incremental learning, and getting above 60 in CFAR 10. That's a impressive place to be.
Thank you.
I have my first question, and you may have mentioned this, so I apologize, but what is the I guess memory complexity compared to like something like online elastic weights consolidation? Like in terms of the number of parameters that have to be stored total, is it more but bounded in the same way, or
yes?
Sorry if I missed that.
No, it's a really, very important question. So it really depends. So this is our hypernetwork, and these are the parameters of our hypernetwork. And as I said at the beginning, what we make sure for fairness is that we always choose a hypernetwork that has less parameters than the corresponding main network. So in our case, but this is our design choice, we always, in order to store this checkpoint, we store less than W parameters. And for instance, in EWC, you need to regularize towards the previous map solution. So you need to also store W. So we more or less store the same amount or even less parameters than online EWC. But this is a design choice. You can be, in our paper, you can be very flexible with how big you choose the hypernetwork.
Yeah. Okay, great. I don't see any other questions, do I?
I got a question.
Yeah, please go.
Yeah, thank you, Christian, for your very interesting presentation. I had actually a question regarding this weight storage for previous tasks. So as far as I understood, the weights that you're storing for replay in the regularization part is the same size as the whole network weights in terms of number of parameters. So if I think one potential baseline, maybe you've already compared it, but one potential baseline to compare with would be because you're storing a whole network for every previous task in your task incremental setup. What would be the?
Sorry, we're storing not for every previous task. We're only storing one hypernetwork, which can generate networks, which can generate solutions for every previous task. So we're only storing one network, not for every previous task.
So when you do the task, when you do the regularization for the regularization part, when you compare the current model, the current hypernetwork with the previous one, shouldn't you store a separate weight for every previous task?
We are comparing hypernet outputs. Sorry if I wasn't clear about it. Sorry, where is it here? So what we are comparing, so we need one, we have one current hypernetwork, we have one checkpointed hypernetwork, and then we're just plugging in different input embeddings of previous tasks to compare the outputs at these particular locations. Okay, so this could be the previous hypernetwork that you checkpoint, and then at this location for this input embedding, you compare your new hypernetwork with the output at this location with the old hypernetwork. So there's only one hypernetwork you always need to have in memory, the one from the previous task.
Oh, okay. I thought that you store one hypernetwork for every previous task and you compare it to that one.
No. Only one hypernetwork is checkpointed. Only the one right before learning the
okay.
task.
Yeah, because okay, thanks. And I just had also another question for the experience replay model that you are comparing with. Do you think that it is fair to compare it with compare a Bayesian model with a deterministic model in terms of uncertainty-based task inference? Did you already also compare it with experience replay? With a Bayesian model with experience replay training regime.
You mean something like variation and continual learning, where they originally proposed to also use corsets?
Yes, something like that exactly. So so in terms of task inference, actually detection or estimation.
So importantly, these methods don't require this explicit task inference, right? Because, for instance, if you do this typical Bayesian continuum, which I call prior focused learning, you learn one single shared posterior. So you have, in a sense, one main network with parameter uncertainty that allows you to make predictions on all tasks. And also in experience replay, you train one model continuously on pseudo data from all tasks you have seen so far. So you never need to explicitly do task inference. Do you know what I mean?
Yeah, I was mainly thinking about a multi-head model that you train in task. So in that case, without giving it the task ID of the head, and then it would be something equivalent to compare to. So
exactly. This is a very good question. this is what we compare to in our paper. For instance, EWC, in task incremental learning, you usually have trained it with a multi-head, but then for class incremental learning, you consider a single shared head. But what we propose in the paper, and as far as I've seen, we're the first, we train EWC in a multi-head setting, but then use uncertainty to infer the head. And on split MNIST, this boosts the class incremental accuracy from 20 to 50% for EWC. On split cipher, unfortunately, you don't see a boost in performance anymore, but yeah, we have this all in the paper.
Yeah, okay, thanks.
Thank you.
Anybody else? I'll go ahead and ask one. Did you try scaling this up to like CFAR 100?
Yeah, we have Cipher 100 accuracies in the paper, in the appendix.
Appendix, okay.
There, the trend becomes reversed because approximate inference becomes more difficult. Then the deterministic solution works better because just the Bayesian approach, at some point, the scalability becomes an issue. But yeah, we still get good performances. I can't recall them now out of my head.
Well, I was wondering because CFAR 100 has the option to explore, I guess, how the tasks are created, like natural task distribution shifts. So I'd wondered if you did, for example, 20 task incremental learning on CFAR 100 with random classes versus using super classes for splitting. I was wondering if y'all had considered like the distribution of tasks, I guess, and how that affects your inference and uncertainty. So, for example, if you did super classes to organize your tasks, prior work has shown that like changes the performance a little bit. And I was wondering if that could be something that like your model or your method could take advantage of more natural classes compared to just these random shuffled classes that we have, these toy problems.
So that sounds very interesting. I honestly don't know the work you're referring to. Did we do the standard thing of looking at 10 tasks, 10 classes each?
Right.
And looked at this as a benchmark, but we haven't explored what you said. That's.
I just wondered if that would like showing that if your method would be able to better take advantage of natural distribution shifts or natural tasks.
It would definitely be interesting to explore.
You have a question from online that says, the approach is very interesting. Thank you for the presentation. Would it be possible to have a single class per task?
Not in this framework, because we currently rely on having a discriminative model per task, and a discriminative model doesn't make sense if you have a single class. But you can, as I said at the beginning, also what Guido van der Ven explored in his recent paper. If you go back here, you can use a hypernetwork to learn individual generative models. That's also what we did in the original paper. But if the generative model allows you explicit density estimation, you can use, just like Guido in his generative classifier paper last year, you can use those to use Bayes rule to design a Bayes classifier that then you can really have just one class per task, and at the end you're able to do discrimination. So I encourage you to check out the paper by Guido. I think it's called Generative Classifiers for Continual Learning or something like that. And he learns separate generative models, but you could also entangle all of them with our approach in a single hypernetwork so that you don't have to store separate models.
Okay. And I'm not very clear on your follow-up question, Tim, so maybe we can ask that offline or something. I have one last question from myself.
Yes.
Is this code released?
Yes, the code for everything is online.
Okay. Sweet.
And actually, as I tried to advertise before, we also
package,
out of this code base, we also made an extra package that allows you to easily explore ideas regarding hypernetworks, because you can do many cool things with them, and I think it's quite useful to have that available in PyTorch.
Great. Any other questions? Awesome. Well, I guess thank you for this wonderful presentation, Christian. This was great, and it'll be available offline on the Continual AR seminar YouTube channel for people to look at later. So thank you again, and I guess join us next week at the same time, everybody. We'll hear another paper, Natural Continual Learning, Success as a Journey, Not Just a Destination. And yeah, great. Thank you, and I guess we'll see everybody next week.
Thank you so much. Thank you so much for having me. Have a great week.
Claps.
Thanks. Thanks. Ciao.